Okay. So now with all the exam Q&A out of the way, let's get back to regression. Because that was fairly quick, that how we went through it last time. And so I figured I might as well just, cover some of the basic parts again today. So remember what we had is we said, well, in regression, so after all in regression, we don't have, classes 1 and minus 1 anymore, or, multiple classes, but we have real values. So for instance, you might want to predict tomorrow's stock values. So then I have real numbers. They're actually a little bit constrained insofar as those numbers are not going to be negative, because owning a stock should never be a liability. The company will go bankrupt before that happens. So it's not entirely true there, but in some other cases, you may very well have negative values too. Then the problem is that, minimizing a loss of this form here, where it's basically, just a discrepancy between the truth y and my estimate f of x. Well, since I don't really have that full distribution p of x and y at my disposition, what I end up doing is I compute an empirical average. So this is like the training error, right? We've already done this before in practice a lot. So this is just formalizing things. And now, since minimizing the training error on its own will lead to horrible overfitting, remember we had estimates of that form where then, if these were, the points to regress on, you might get an estimate that looks like so. So to, prevent this from happening, you actually need to add a regularizer here. And this regularizer was basically a means of controlling capacity, as in keeping the function simple, like, for instance, keeping the coefficient simple. And again, that was actually already done a little bit in homework 1 or 2 when we looked at penalized regression. Okay, so this is nothing new. Let's look at a few loss functions here. This is one that we all know. So minimize the least mean squares deviation between truth and, well, estimate. So if you look at the gradient of this, it's actually quite an interesting object, right? The gradient of this, and I'm just going to superimpose another 0 axis here, and here's 0, is going to look like so, right? So basically the gradient is going to be y minus f of x, actually minus that, right? It's basically f of x minus y, so it's the deviation between my estimate and the truth. The L1 loss, this is just an absolute value deviation between what the truth is and what I end up estimating. It actually has a fairly interesting derivative, right? The derivative, if this here is 1 and here's minus 1, then the derivative looks like so. So in other words, it is the sine of, well, f of x minus y. So in other words, my gradient is heavily bounded, but I don't really have much control about the magnitude of that deviation. So therefore, if I end up optimizing, basically it doesn't really matter whether I'm here or whether I'm close to there. My gradient will always remain the same. Okay. Then there's something called the epsilon insensitive loss, which is basically the previous loss, but just with the bottom chopped off. So this part here is different. Okay. And that, of course, has a derivative that looks quite interesting. Let's just draw the derivative, and it's basically just that. Negative, it goes to 0. comes back up again. And here's epsilon. Right? So that will lead to support vector-like expansions afterwards, because basically all the points that lie within that epsilon, basically all the points that lie within here, will not contribute to the actual solution. So the simplest thing that you can do is you can solve the optimization problem where you say, well, I want to minimize over W, right? Just, a least mean squares objective plus a regularizer. Then if you actually go and solve this, you get exactly the equation out, which is something that we already saw before. Now, in terms of means of how to optimize that, conjugate gradient might actually be quite useful, and this is something that we went through in the recitations. Right? So this was the optimization part that was covered in the recitations. Yes?
If you have a case where you have very good data that looks very linear, for example, and a few outliers that would make, let's say, if you forget about the regularization term, that would make the slope of my line very off compared to
right.
Would adding this term basically make
yes.
it more robust to outliers?
Yes. So adding regularization will do precisely that, and there are actually two ways on how to deal with it. So let me quickly show you a picture of what else you can do. Because there's something called Huber's robust loss, which is specifically engineered for that purpose. Okay. So basically, if you think about it, one of the problems with squared loss is that you have this 1/2 basically y minus f of x squared, right? And the problem is that its gradient is unbounded. So if I have some outliers which are really, really far out, then they will contribute in quite unreasonable manner to the gradients. So if this is basically f of x minus y, this could be large. Now, how can I actually address this? Well, one really nice thing would be if we could say, well, I actually like this gradient, but I don't like it to exceed a certain threshold. So what I'm going to do is I'm just going to clip this gradient. And so instead, so I'm going to take some loss function. I'll show you the loss function in a moment. So I'll have some loss function of y and f of x. And I want to make sure that L prime of y and f of x happens to be clip. So this is just, min and max trimmed on either side by some coefficient. Let's say we call this sigma here of f of x minus y. Okay. So now let's figure out what this function should look like. So what we can do is we can just go and integrate this function here by parts. Right? So, well, first of all, we can assume it has to be symmetric. Right? It's a, self-respecting loss function, and without loss of generality, we can assume it's symmetric. Furthermore, we can assume that at the value 0, it has to be 0. Right? Okay. So a constant negative derivative simply means, well, let's draw this function, right? That it's going to decrease linearly. Then here at this point, let's call it sigma. Actually, let's put sigma in here a little bit further. You'll see for a moment why. Okay, let's make this sigma. It then changes its slope. Basically, its slope starts decreasing. Now, this part, we know the stem function of a linear function is a quadratic function. So we basically get the parabola. And now you see why I moved this over, because I screwed up drawing things first. And then at this point here, where we are again at sigma, the slope doesn't change anymore, so I get this. So in other words, I have a function that is linear here and quadratic there. This is actually called Huber's loss function. And essentially it works as follows. This loss function here equals 1/2 y minus f of x squared, provided that, well, this is basically if y minus f of x less equal than 1. And here we have y minus f of x minus 1/2 otherwise. That's basically what I engineered. And I just set sigma to be 1. Right? So you can immediately see that this gives me a nice continuously derivable, differentiable objective function. It's linear, quadratic, and linear. And it does exactly what you asked for, namely it will limit the influence of outliers. Okay. So there's something called the trimmed mean estimator. And that is exactly where this comes from. So the trimmed mean estimator is something where you take the mean, but you do so after throwing away the largest and the smallest terms. And it does this exactly with the losses here. This trimmed mean estimator is ancient. So it's probably 400 to 500 years old. So here's where it first occurred. When you needed to distribute length measurement units in the Middle Ages, they didn't really have a terribly well standardized system of, let's say, what 1 foot is, right? So they didn't have like a reference foot that was stored, with the emperor, and then they would make copies and distribute it. That's not how it happened. This happened a lot later. So, however, they wanted to have a reasonably reliable definition of what 1 foot meant. And the rule went something like that, and I forget the exact numbers, but it basically goes as follows. Pick the first 12 men who walk out of church on Sunday. Okay. Send the 2 men with the shortest feet home. Send the 2 men with the longest feet home. Have the remaining 8 men line their feet up. Take that length, divide it by 8, and you have a reference for 1 foot. This is a trimmed mean estimator, and this was quite relevant in the Middle Ages because you would actually have people with crippled feet, right? So you really want to remove those outliers. And yeah, that gives you a good trimmed mean estimate from the population, which is robust against at least 2 people having no feet and 2 people having feet that have been maybe extended by some unnatural means. So this is where statistics started. And so Huber in 1962, something around that time, showed that this overall, or more generally, you take any loss function and you basically cap its slopes, will give you robust estimates. So robust estimation basically means that if I give you data and I corrupt it, that up to that point, up to the breakdown point, corrupting the data will not change my estimate substantially. Who has heard of similar things before? Okay, so there's one place where you may also have heard of that. It's in the context of privacy. So differential privacy, and I don't have time to go into this in detail, is basically a requirement where you essentially assume plausible deniability. So what you want to make sure is you have an algorithm where whether you're in the data set or not doesn't really change the outcome too drastically, at least not with high probability, such that nobody can prove that you were a part of that data set by just looking at the outcome or infer things with high precision about your preferences. Right? And again, this requires robustness in the estimate. Okay. So I hope that helped a little bit with the context of basically robustness. Okay. Yeah. So then let's have a look at what happens. So we've already gone through the proof of the representative theorem on Monday in a fair amount of detail, so I don't need to go through that in a lot more. But just as a refresher, the idea was essentially that if we go to a feature space, those phi of xi's span a finite dimensional space. And so therefore, in order to get a good estimate of W, I only need to get an estimate of W that lies in the same space, because everything orthogonal to it doesn't really matter. And that regularizer here will make sure that it's regularized away. That's essentially the proof of the representative theorem. And then you can go and plug that back in, and you immediately get the solution. The reason why this is really great is because now you can solve optimization problems in infinite dimensional spaces and get a finite solution out of it. This is quite amazing, because usually when you do splines and so on, you think, well, as I'm increasing the number of dimensions with splines and so on, the number of coefficients will, increase. Here, the statement is that as long as my data set size doesn't explode, things are actually pretty good. Okay. So in support vector regression, we get exactly that scenario that I described before, where we had this epsilon insensitive loss, which was insensitive here. That's not exactly the world's best idea for a loss function, but okay. You can go through the math and you get a dual optimization problem out of it. I'm actually going to skip this because it's just a lot of algebra in public, and the algorithm isn't quite so amazing. The issue is basically it ignores small typical instances with small errors, and you get interesting optimization problems. Let me just quickly show you how it works. So if I have data, so this was the original data, then if I put an epsilon insensitive band around it, it'll basically, require that I only approximate the function with that epsilon precision. And this is why I get the red estimate as opposed to the green envelopes that were the actual data. Okay? And the larger I make this, the flatter my estimate becomes. Right? So here you can see that the estimate is almost a constant function, because I can get away with it. And, pardon? Sorry, can you speak up? I'm having trouble hearing.
Is it sample?
Okay, so what are the inputs? Okay. The inputs in this case would actually be, well, these or these, would be actually these or those points respectively, or actually rather, it's that point here. What I've done is I've just visualized the inputs plus and minus epsilon, right? So the real input would be always the sinc function, right? It's basically this thing here. And then I've just, visualized it plus and minus 1/2. And so what I end up doing is I end up estimating, well, the smoothest function that fits into this envelope, which is what we have here. And basically what you will see is that those points that are exactly where this boundary is being hit, that these are exactly the support vectors. And of course, the narrower I make this, the more points I will hit, and conversely, if I make it really wide, this is probably the 1/2 example, then there are only really 3 points where I end up hitting something.
So what is the function used to fit these points?
So that is, in this case, a Gaussian radial basis function. So this is,
No parameter.
well, okay, well, the parameter is, in this case, the function itself. So it's basically f of x is the inner product between phi of x and w. And so what you then get is, of course, that this afterwards will become a sum over alpha I k of xi and x. All I did is I just skipped over the details of the support vector regression derivation, because I think actually the Gaussian process regression derivation is going to be a little bit more useful in terms of practical applicability. But if you want to go through it, all the details, all the math is in the slides. So, okay. Any more questions? Okay. So here's exactly Huber's robust loss. This is what we talked about before. This is the trimmed mean estimator. Right? It's linear here, quadratic there, linear there. Okay. That brings us to the end of support vector regression. Let's look at novelty detection. And we'll look at another regression estimator in the Bayesian context, and that one is going to be possibly slightly more usable. Okay. Any other questions so far? Okay, good. Novelty detection. So basically, well, what's the question? The question is, well, let's say we observe some data. And that's maybe drawn from some distribution, some unknown distribution, like network usage patterns, handwritten digits, alarm sensors, factory status, basically, something that your computer might be doing. And what you want to do is you want to find unusual events, or clean the database, or distinguish typical from unusual observations. To be more precise, if I have a database of handwritten digits, I might want to find the really horribly badly written digits. Or if I'm interested in computer security, well, all the known attacks I can actually easily safeguard against by just scripting a rule, having a recognizer for a specific code signature, and then deploy that. So in other words, if a virus is out in the wild, I've identified it and it has a certain signature. So and this is basically what all the antivirus companies are doing. This is why you get an update for your antivirus definitions every couple of days, because a new virus has been discovered, they add it to the signature set, and that's it. Now what happens if something new comes along? Well, you may not know exactly what it is, but you can surely tell that your computer is behaving strangely, right? Likewise, if you have a server center somewhere and you want to actually make sure that you're safeguarded against unusual failures or unusual behavior, you might actually want to have a novelty detector that will tell you, well, look at the server center, something strange is going on. I don't know what it is, but it's strange. Okay. So what are strange events? Well, strange events are those that have very low probability of occurring, right? They are basically, very rare, very unlikely things. And if I end up seeing them disproportionately frequently, I know something's wrong. So the task, therefore, is, well, get something like a density estimator, except that the task is a little bit simpler. So in a density estimator, you want to do well and estimate the density for all the observations that you're seeing. Here, I don't really care about doing well in the high-density regions. All I have to say is, well, yeah, that's typical. I don't really care about how specifically typical it is. But I want to have a mechanism that tells me very easily how untypical something is if it's below a certain threshold. This is a much easier task because first of all, I don't care about the high density regions, which is where usually most density estimators spend a lot of their capacity on. Secondly, I don't actually need a density. If you give me a density multiplied by 42, right, it's still okay. I just need a different threshold and all is fine. So it doesn't have to be normalized in any meaningful way. It might look like a density sort of kind of, but it doesn't really have to be one. And that's what makes novelty detection a so much easier problem. So, a few more examples. So network intrusion detection, we already talked about it. Jet engine failure detection. That's another example where it's really, really hard to, well, basically find a lot of failure data. Because those engines are ridiculously expensive, so you can't just go and blow a few of them up to find out all the different ways how they might fail. You might do that for one or two, but you're probably not going to cover all the failure modes that such a jet engine might cover. Right? Fraud detection. Well, it's not like credit card companies are amazingly good at it, but if you all of a sudden go and place a hardware order for, let's say, $7,000 because you need to buy more computers for your lab, and you do that at midnight, then your bank will contact you and ask you, Alex, was this transaction okay? That just happened to me 2 days ago, right? Of course, because usually buying hardware at midnight is a bad idea because, well, that's not usually when people spend a lot of money, and on top of that, this was with a vendor that I hadn't used before. Okay. So this is where, basically novelty detection comes in because it's unusual behavior. Another thing are self-calibrating alarm devices. So if you think about a car alarm, you usually have that interesting tension between, well, you want to make it as sensitive as you possibly can, right? Because otherwise, the burglar gets in, steals your radio and walks off, and the alarm doesn't go off. That's not good. On the other hand, if you make it amazingly sensitive, then a truck drives by and the alarm goes off. And that's significantly infuriating for all the residents near that street where the car is parked, right? So wouldn't it be nice if you had an algorithm that automatically adapted to the environment? So in other words, if I park the car on a noisy street, well, the alarm will become less sensitive, and if it's parked somewhere on a quiet street where nothing ever happens, it'll be super sensitive. By the way, somebody please build that device, put it up on Kickstarter, I'll buy it. No, seriously, this would be a really cool hardware project. And the home alarm is actually similar. I mean, people spend a lot of money calibrating their home alarms for, let's say, animals. And if I don't have a dog at home, I actually want the system to go off if some small creature runs around wild in my house. On the other hand, for people who have a dog, this is bad. So you basically want it to be automatically calibrating, right? So can we build such devices? And it's actually not that hard. Again, put it up on Kickstarter, build it. So here's how you could do novelty detection, right? So the simplest thing that you could do is you just, well, say novel data is the one that we don't really see very frequently. It must lie in the low density regions. And so step one is, well, let's estimate the density. We could do that with Parson windows, right? We've already looked at Parson windows. We've, designed corresponding density estimators, so all is good. Right? And this gives me this thing here. And then what I do is I just pick those observations xi with the lowest density. And I say, well, they're probably unusual. Right? So I could do that. So let's see what actually happens. So what I did is I took some handwritten digits. These are USPS digits. So there's the USPS repository of handwritten digits, about 4,000 digits. It's quite worthwhile playing with it. And I just took the unnormalized density because I don't really care. And just sorted things. And those are probably the ones that are quite uglily written. But what you can already see is there isn't like this huge gap in terms of values, right? It's just, nice and continuous. So in other words, do you make the cut here or here or here? There are a couple of digits that are very cleanly written. And if you look at them, that's what it looks like. This is typical data. That's data from, the mode. And you can already see that this algorithm doesn't work terribly well because you get something like this. And, well, with this guy here, probably somebody wrote the 3 on a line and it got cropped kind of badly. But, yeah, it's okay. This is really ugly data, right? These are ugly digits. And basically, ugly in this case usually meant somebody wrote something with a Sharpie pen, right? So basically, there was way too much ink there. And yeah, not quite sure what those two are. It could be, yes. But basically, yeah, okay, it finds ugly data. But can we do better? So, a couple of things. We don't really care about getting the high density regions really well. We only care about the relative part, and we only want to get a certain fraction of observations. So can we actually exploit those three things to design a better estimate that's better quality, that actually has better guarantees? And so we're explicitly going to do that. So we only really need a level set. And so we basically use a proxy for P of x. And we'll just go and find some P of x that's less than a threshold. So let's see what happens. Just a moment. Let's actually look at the picture first. So let's say this is my density. Then thresholding means that I don't really care about this region here, right? I don't really care about how typical it is. What I'm mostly interested in is this part, and this part, right? Secondly, I could actually go and use a different estimate which looked like this, right? Whatever. And now I have a different threshold, right? And, okay, so I drew this part badly, but these two lines, that's actually how it should go, right? But basically, what you can see is, if I rescale things, stuff shouldn't matter. So both rescaling and also the high density regions are, the algorithm should be impervious to that. So let's first look at, density estimates that I could use. So we could use Parsons windows. We could also use exponential families. So remember, in exponential families, well, we have some sufficient statistics phi of x, and we have some parameter theta that we want to get. And so, you have P of x parameterized by theta is e to the phi of x dot theta minus g of theta. So this holds for Gaussians, this holds for multinomials, holds for whatever. And then I can happily go and, write the negative log likelihood. This is minus log of P of all the data given theta. This is minus log P of theta. And I happily go and optimize the sum of those two. Well, plus a constant, of course. Right. But that constant doesn't matter. Now, this is all very nice, but the normalization, this g of theta, can be painfully expensive to compute. It can actually be NP hard in some interesting cases. And as said, we don't have to do terribly well for high density regions. So how do we fix it? We basically go and convert the problem into something that, at first glance, looks super complicated. So instead of looking at minus log p of xi given theta, I'm going to threshold this. So I'm basically going to use a reference density. Let's call p naught rho minus g of theta. And what I'm saying is that whenever p of xi given theta is greater than that, I don't really care. When it's less than that, I care. So therefore, I take the ratio between those two densities, p over p naught, this expression here, take their log, and now when that ratio is greater than 1, I don't care. When it's less than 1, I care. So therefore, I take the negative log and take the maximum of that. Now, the decision to include g of theta was quite deliberate, because that's the ugly part in the entire inference problem, because usually this normalization is very expensive to compute. So this can be actually NP hard. Now, since I'm using this normalization also in the reference threshold, just very conveniently, both terms cancel out and everything's okay. By the way, if you have a question right now, don't post it on Piazza right now. You can actually ask me directly in class. So please ask whoever it is. I don't know who it was, but if you have a question, please ask it now. Guys, I don't bite. Yes?
It wasn't a question about this in particular, so
Okay.
it's a question which can be answered.
Okay, good. Okay, good. Okay, thank you. And thanks for, raising your hand. Thank you. I much appreciate that. So basically what happens is the ratio between those two terms makes exactly that log partition function go away. And that's just because I included it in the reference as well. And so now I don't have that NP hard term anymore to deal with. So now I just end up with a maximum of rho minus some score. And I end up optimizing this. So this is now a very simple quadratic program again. By the way, why is it a quadratic program? Any ideas why this is a quadratic program? Yes?
We're quadratic in theta, which is what we're optimizing over.
Yes?
And we have, depending on how you want to formulate max, that can be seen as a constraint.
Exactly.
Something like that.
Exactly. That's the perfect answer. So what happens is that the maximum here, this term here, I could also write this as basically some variable psi I, and I would then have, well, so now the objective function is a nice quadratic term, and I would now have something of the form psi I greater or equal than 0, and also psi I greater or equal than rho minus phi of xi. Sorry, the stylus doesn't let me write that final resolution. Sorry, this is the handwriting of a 5-year-old. But basically, what I can do is I can turn the max into a linear term and a constraint. And this way, I'm now in the context of a quadratic program that I can easily solve. Well, or at least that I can then transform and do the usual things with it. So the nice thing is that this problem is much simpler than density estimation. And it gives you something that only works, that focuses on low density regions. Now what you can do is you can also derive the very same problem using geometry. As a matter of fact, that's how we first came up with this idea. We first thought, because we were doing, support-aware classification, then I think over coffee we were joking, well, what would happen if you were to do one-class classification? And then once we'd asked the question, deriving the algorithm was kind of easy. But yeah, basically when you do research, it helps sometimes to just, basically start asking stupid questions. And it was so outrageously silly that it actually turned into something useful. Yeah. So here's basically what happens. You could say, well, in order to classify whether something is novel, I want to minimize, w squared. So in other words, I want to push this margin, this boundary out. And I want to separate all the data from the origin. So by setting w.xi greater or equal than 1, that's exactly what happens. Now, question, why do I not need a constant offset here? So why is it a bad idea to add, well, b plus? What would happen if I did that? Look at the optimization problem. What would happen if I added a b? Yes?
That wouldn't really give you much of a constraint on W because you just make E bigger.
Exactly. Perfect. So what would happen is I could then actually set W equals 0 and just pick B to be whatever, like 1. And the problem would be trivially solvable. So that's exactly why you cannot have a constant offset here. Okay, so let's get rid of the b again. Now, when you cannot satisfy all the constraints at the same time, you're again going to go and add slack variables. So you're going to add those psi's. And that gives you an optimization problem, which, if you squint hard enough, you'll see is the same as this one here. So by rewriting the constraints into a max, you get exactly the previous problem. Okay. So now let's go and look at the optimization problem again. So it's exactly the same handle cranking as what we did before. So minimize 1/2 w squared plus c times sum of the psi's. If c is really large, it means that I want to make sure that all the points are on one side of the boundary. Or in other words, in the context of the threshold density estimate, it means I really care about the density estimate rather than the smoothness. And well, then we go and just write out the Lagrange function, right? So the blue parts are the objective. Yes?
Where does the green come from?
Where does the green part come from? Well, the green part was exactly the set of constraints, right? There was this guy here. Those are our constraints.
Yeah,
right?
where does it?
Well, that's basically, if I want to make sure that all the red dots here are to the right-hand side of this, of this hyperplane, that's exactly this constraint, right? So w.xi greater or equal than 1 is the hard margin part. And if I want to actually give things a little bit of slack, I'm going to relax those constraints, but I need to pay for them here. And another alternative way of seeing it is that this would be basically the corresponding constraint set, right? So if you look at those constraints, they look exactly the same thing as before, except that rho equals 1. So if you plug rho equals 1 in here, you get exactly the same optimization problem. Okay, thanks for asking the question. Any other questions?
Blue dots.
Pardon?
So you ended red dots and blue dots.
Okay, so the blue dots are basically new observations, right? And what you want to make sure is that, here, the slightly weird definition of novelty is everything that's on one side of the half space is typical. Everything that's on the other side is novel.
So they're not participating in this.
Exactly. Now, whether that's a good idea is a very different question. It turns out you can prove a fair number of alternative ways to formulate the problem that will lead to the same optimization problem. For instance, you can set it up as a minimum enclosing sphere problem. You can set it up, as I already did, as a thresholded density estimation problem. And they all give you the same optimization problem. So that's why it actually turns out to be a less weird idea than originally thought. Now, if I had the soft margin case, then this blue dot here would probably, correspond to a slack variable, and this one would be just fine. Sorry. Okay. Now let's look at the optimization problem. So remember we had the slack that comes from the fact that not all constraints might be perfectly satisfied. That's the green bit. Right? And then we need to make sure that you cannot make up for screwing up some instances by doing really well on others. Basically, no bonus points, and that's this constraint here. Okay. And so now you have the Lagrange function, and you again crank the handle just in the same way as you did before. Namely, we will need to get derivatives dw, and we'll need to get derivatives d psi. And then we're done. Yes?
How would you do this in an online setting if you haven't listed?
Okay. So in an online setting, you would actually resort back to the formulation that wraps the constraints into a loss. So this is basically what we had before with max of some difference and 0, right? And then basically for every new observation, you would basically compute the stochastic gradient of this and update. As a matter of fact, we're going to do stochastic gradient descent updates quite a bit more also in the optimization part later. So that's a very, very valid question. So you could use this to identify whether observations are novel and at the same time use it also to update your model, which is a very sane thing to do if you're, let's say, a network sysadmin and your network traffic will change slowly over time. You want to adapt to that, but at the same time, you want to make sure that if something very unusual happens, that you'll actually inspect it. Okay, so now we just take derivatives as promised. We get exactly the same type of expansions again. So the main difference to the standard SVM problem is that we don't have any labels anymore. And yeah, so this is exactly the same objective, just that we don't have any yijs, and the same type of constraints. And this works well because the primal problem was convex, and so I can happily go ahead and do this. Okay. So here's yet another way of looking at the problem. So remember that for things like the Gaussian RBF kernel, so in other words, a kernel of the form k of x and x prime equals e to the minus 1/2 x minus x prime squared. Yeah, so basically for a kernel like this, all the points have equal length, because k of x and x equals 1 in all of those cases. So all the points, therefore, lie on a ball, like here. Furthermore, I know that the angle between any pair of points is less than 90 degrees. So I therefore have a nice half space which contains all those points. Now, since they all lie on the surface of a ball, and if I go and push the hyperplane out, what I'm going to do is, if you think about it, I take a ball and I slice it off, think of an orange and you're slicing something off. Well, what happens is if you look directly onto that slice, it's basically another circle. So you'll basically, by slicing a ball with a hyperplane, you will get a ball of 1 dimension less. Right? Very high dimensional spaces, but yeah, geometry still works. And so what you basically end up doing is, by pushing that hyperplane out, you're going to make that ball smaller and smaller. So it's effectively trying to compute the minimum enclosing sphere that contains all the points. And that's what's happening here. So that's basically the third interpretation of the same algorithm, at least for some data. Mind you, the minimum enclosing sphere problem is also a quadratic program, and you can derive it just as before. So they are basically the center and the radius are the two variables that you need to optimize over. Okay. Now, there's one last thing that we need to address. Think back of this poor systems administrator. If that poor systems administrator gets about 200 warnings a day, he's going to just uninstall the program, right? Because he'll go crazy. But you can ask the sysadmin, well, you know, how many warnings a day are you willing to get? And he'll probably say, yeah, maybe 10, and maybe with 10, I'm happy to follow up on those. But he probably won't follow up on 100 or 1,000. He'll go crazy. So wouldn't it be nice if we could actually set up an optimization problem in such a way that the fraction of points that are considered novel is actually predetermined? So in other words, I'm essentially going to ask for the bottom quantile. And if you look back at the previous example here, well, if I say took a hyperplane that was a little bit further out, well, okay, that's too far out, but I guess you get the idea. Okay, maybe this one will work. You'll see that basically this will slice a different fraction of points. So in other words, by making the constraint w.x is greater or equal than rho for a suitably chosen row, I can actually quite easily determine how many points are on one side of the hyperplane and how many are on the other side. Except that, of course, I don't know rho. So what's easier than that? Well, I just make rho itself a variable of the optimization problem and have the algorithm find it. Okay. So this is sometimes also referred to as the new trick. Sorry, let me use a different font color. New trick. The history of that being, we first had the optimization problem, and then I think we spent twice as much time thinking about how we would call the Greek that variable. And yeah, okay, it was a bad pun. Yeah. Because it was a new support vector machine formulation. So, duh. Okay, so here's what happens. Basically, before that, we had a 1 in the constraint. So remember, before that, we had basically something of the form greater or equal than 1 instead of this greater or equal than rho. But what I now need to do is I need to actually optimize over rho itself. And if you think about it, there are two constraining things that you want to do. Well, each individual constraint, of course, would like to make rho as small as possible. Because if rho gets smaller, then the contribution from the corresponding slack variable psi I is also smaller, so I have to pay less. So the smaller rho is, the easier the constraints become. But on the other hand, I want to make sure that overall rho isn't too small, so I basically add it as a negative in the objective. And I'm multiplying this rho by two coefficients. One is the sample size m, and the other one is this variable nu. And what I'm going to show you in a moment is that choosing the value of nu between 0 and 1 will give me a fraction of nu points that are on the appropriate side of the margin, or that hyperplane. Don't worry, I'll walk you through that in detail. But the first thing is, if you actually work out the optimization problem here, then we get almost the same problem as before, just with one key difference. And that is that now we have a constraint, sum over alpha I equals nu times m, and that the linear term has vanished from the objective. Well, the fact that the linear term vanished from the objective is kind of trivial, right? Because, well, if you look at this term here, right? If I have that sum over alpha I equals, some constant, then I might as well drop it from the objective, which is basically why you can actually do this. Okay? And now we have this constraint, sum over alpha I equals nu times m. And the alpha i's are between 0 and 1. Okay. Now, you can immediately see that in order for this to hold, I need to have a sufficient number of alpha i's that will actually be non-zero. So if nu is, for instance, 0.1 and m equals 100, so then I get sum of the alpha i's equals 10. Now, since each of the alpha i's can only be at most 1, I need at least 10 different alpha i's to be non-zero for this sum to hold. And since these are exactly the support vectors, the points on the boundary on the wrong side, well, you can basically make that argument. So here's this a little bit more formally. Let's look at the optimization problem, and let's assume that W is fixed in some way. So then it's very clear that the psi i's will always try to be as small as possible relative to this constraint here. Okay. So what happens if I increase rho to rho plus delta? So what happens is that out of those constraints here, so let's assume that I have m minus where the constraint is satisfied. I'll have m0 where I basically, okay, so here I have a strict inequality, here I have an equality, and I have m minus. These are the points which are already on the wrong side. Now, if I increase rho, basically I'm tightening up the constraint, then those two terms will need to increase. They will need to lead to increasing psi i's. And so therefore, I get the corresponding optimality condition that, m0 plus m plus times delta has to be, well, for optimality, this has to be greater than, well, actually, let me just go back. All times delta plus m times nu times delta. This has to be greater than 0. So in other words, I'm making things worse if I'm picking this. And so by working through the constraints, you get that, basically nu has to be less than m0 plus m plus. Likewise, if I'm relaxing the constraints, I will get the same inequality for m minus. By doing these two things, I actually get to see that at most a fraction of points of nu are novel. Okay, let's see whether there's a little bit more math there. Okay, this is exactly what I was arguing for. So basically, if I make the threshold smaller, then I am going to pay delta times m minus, so basically all those points on the wrong side. Here's m minus, here's m plus, here's, sorry, here I defined m plus to be the points m0. Okay, so basically if I move this and move it in here, then I end up benefiting only those points where the constraints are violated, m minus ones. On the other hand, I end up paying nu times m times delta in the objective because of the contribution of the margin. And, well, if this is less equal than 0, that's no good. Likewise, if I increase things, then I end up getting m plus minus nu times m. So that's basically the points m minus plus the ones on the boundary. And so I get as a combination this condition here that the number of points to the left side and the number of points to the left side and on the boundary that they contain within its interval nu. Okay, that's the argument. Now, the reason why this is a little bit more subtle than saying, well, a fraction of nu points is exactly on the wrong side of the boundary has to do with the fact that, well, what exactly happens to the edge cases where the constraint just is about to become active when the constraint is met. So, in other words, these points here. Okay. So let me show you a few pictures of how this works. So a toy example is basically, I'm going to go and take, some points just drawn from normal distribution, and let's say I set nu equals 1/2. So if you look at it closely, you'll see that about half of all the points here are outside the boundary. So they are considered novel. And actually, if you run the optimization problem explicitly, you'll see that it's about 54% outside and 43% inside. Now, if I add some more points to it, right? So these are essentially real outliers. Then, well, basically, most of the novelty blame is shifted to them. So if you compare those two boundaries here, you can see that this boundary here is a little bit more inclusive. This is a bit more inclusive. Now, if I actually go and increase the acceptance threshold, so in other words, I only assume that 10% of my points are novel, so nu equals 0.1, then for the same data, it now includes most of the points here, and actually also most of the points there. So it leads to a different assumption of what is considered novel. Now, of course, if I change my kernel bandwidth, I end up with something that is a lot less smooth. So this is basically the same problem as here. So the value of C, let's play the kernel bandwidth. You can see that this solution now here is much more willing to accept points as typical here and there, but then also assume a very unreasonable boundary. Okay. So does that clarify a little bit how setting nu changes things? I think you had a question.
So at each time step, the formulation you gave, you said it's mathematically equivalent to the SVM we had before.
Well, we saw three different formulations. So the adaptive margin formulation, unfortunately, is not directly equivalent to the others, except that you could shoehorn the other ones also to match this, but that would be kind of just awkward. But if you don't have the adaptive margin formulation, then minimum enclosing sphere when all the points lie on the ball. Hyperplane that pushes points that separates the origin most from the points. And the threshold and density estimate, all three lead to the same optimization problem. And so therefore they are formally equivalent. Having the adaptive margin is something that you could do in either of those cases. So if you had the threshold and density estimate, you would simply say, well, I'm going to use a reference density, but I'm actually going to optimize over what exactly that reference density should be. And I'm going to use my reference density in such a way that I pick only, let's say, a 5% quantile of all my points as novel. Okay. There was another question up here. Yep.
So the only reason that this wouldn't work in practice is if we didn't have the features that express the anomalousness of the anomaly. In practice, do we have those features? How does this work in the wild?
Okay. Very good question. So how much feature engineering do you have to do? Well, if you don't have any idea of what good features are, probably life is unpleasant for you. Now, there are ways of inferring good features. So, for instance, what you can do is you can, do effectively cross-validation, right? So you can basically, build your novelty detector on 80, 90% of the data and deploy it on a random subset, remaining random subset of 10%, right? And if your novelty estimates are far different from what you trained it for, it means that you're probably overfitting, right? So typically you would end up considering a lot more things novel there, right? So that's one way of calibrating things. The other thing is that if you end up with a function that is highly complex, so that's the situation here, right? Then, in other words, it has a very large norm in their parameters. That's also usually a dead ringer for something went badly wrong, right? So those two things you can use to get, well, some guidance in terms of what works. Now, if you are able to do good feature engineering, you should absolutely do it. So in other words, if you, for instance, do that for network intrusion detection, you very much want to talk to somebody who understands computer networks to engineer your features. And it's going to be a combination of both things. Now, you could do all sorts of exotic things in your feature engineering before, in the end, you throw a novelty detector on top of it. If you wanted, you could probably have a deep network underneath. As a matter of fact, if you did this right now, you would probably get it published just straight as it is. Because right now you can, if it has deep networks in it, it will get published. And deep networks novelty detection hasn't been published yet, so go and write that paper. Give me an ack in the footnote. And I'm willing to bet you that it will get published. Okay. Yeah. No, it's probably actually a good idea, so why not? Which is basically just very heavy-handed kernel and feature engineering. But I think I'm quite a bit over time. I think we need to cut it short here. We'll look at more details next week. Okay.
About the midterm